regression line. Regression line actually gives the. Can you illustrate what is the regression line?
So the correlation is linear. The best estimate gives the regression line.
Yeah. Yeah, that's very important. We pick this line if there is a linear relationship only, right? So it's not correlation is linear. We cannot say correlation is linear. The relationship is linear. Then of course correlation coefficient will be large and so on. Of course, always it's better to. In this case, you have only two variables, right? Y and x. So easily you can plot in simple linear regression and so on. You can see whether there is a linear relationship or not. So then only if there is a linear relationship you will try, otherwise there is no point of trying it. So the regression line actually can be considered as approximate average y values at different x's, right? So for example, if you consider x and y, so for different x's, there can be several y's. No? There can be several y's. Of course, usually when you collect data, there might be only one or two observations for a given x. There can be only one also. Most of the times there is only one. But we can consider that as one possible sample coming from this kind of set of values, possible values. So regression line actually is supposed to be approximating the averages of y values at different x's, right? So this we cannot expect it is the averages to be exactly on a straight line. So we can say it's an approximate line goes through the averages of y values for different x's. So we didn't talk about the equation yet, right? So what we discussed was when x changes from the average by one standard deviation of x, then y changes on average by how much? R times standard deviation of y. Right? On average, the word on average is important there, right? When x changes. Right? So therefore, we can easily find out the mathematical equation. Right? So if you assume that the equation is a straight line, generally for the fitted line or the regression line, we denote the y part as y hat. Right? That is the fitted value or the estimated y value, because actual y values are everywhere. Right? So the points of the line we denote by y hat. So therefore the general equation is like this: y hat is equal to some intercept plus some slope times x. So what you have to do is to find out the slope and intercept separately. So in mathematics students, you can find out, because already we know the slope. So when x is changed by one standard deviation of x, then y changes by r times by standard deviation of y. Therefore slope is very clear then. Right? Slope is equal to this side divided by. So that is r times sy. And for example, if we change x by standard deviation, so you can find out that. In order to find out intercept, you can choose any point. For example, one we know this line and also SD line, both are going through one special point, x bar y bar point. Right? So therefore x bar y bar point must be on the line too. So you can find out intercept and slope like that using those two properties. So when you do that, slope is equal to r times standard deviation of y divided by standard deviation of x. And because the line goes through x bar y bar point, you can get this equation. From that you can find out the intercept. So you know the regression line. So finally the regression line will be something like this: y hat is equal to y bar times this times, and you can write it in this form. But we didn't still talk about why, how this term comes, for example, why do we say when you increase x by 1 standard deviation of x, y it changes by r times standard deviation of y. We just mentioned it. Actually, what we are talking about here is something called the one particular type of line. Different people may use different methods to find out a suitable line. The definition of the best line, best, may be different from person to person. What we have here is actually something called the least square line, least square regression line. In that least square regression line, we use a particular criteria. So we'll discuss about that a little later. So this is just an example of the regression line. But of course, this is coming from the book. But theoretically, we can fit a line to any scatter, right? But there is a small problem. You can assume that there's a line, you can draw a line. But usually, when you have this kind of scatter, simple linear regression is not the best. Right? One reason is that you can see that the variability of y's at different x's is not roughly the same here. Right? You can see that when x increases, the variability of y changes. Right? But in the least square method, when we use the least square method to find out the straight line, so-called best line, we have an important assumption that the variation of y's at different x's is roughly the same. So if you have that, if that assumption is satisfied, then of course the least square line is the best. But in this kind of situation, it is not the best. But still, the book has used this particular example to show how to get the regression line. Right? So for this, we have the sample mean value for x and y. Right? So this is the education versus, the income versus the education. The amount of education, level of education. So once you know the standard deviations and the averages, of course you can easily find out the slope and the intercept using the formulas. So thereby you have the formula, regression formula. Once you get the formula, of course, when you know the slope and intercept, we should be able to interpret the values also. What, for example, here the slope is equal to this 2176 and intercept is equal to this value is a negative value here. So what do they really mean? Right. In a usual mathematical straight line, right, if you have x and y, if you have a straight line, in this case y is equal to a plus bx, what does this b mean usually in a mathematical sense? Slope, the meaning of slope, practical meaning of slope.
Gradient of the gradient.
Yeah, that is one way to say it. But if somebody doesn't know about what the gradient is, you can easily explain it in a simpler terms. Is actually the change in y if you increase or decrease, if you change x by 1 unit, right? If you increase x by 1 unit, y will change by b amount. So that is what the slope is, right? That in a mathematical equation, in that case we are considering all the points on the line, right? So if you increase x by 1 unit, right, if you go like that, then the amount that goes up is b. That is what the mathematical interpretation of the slope in mathematical sense. But here it is actually slightly different. One thing is that you cannot talk about increase, you cannot say if you increase x by 1 unit, for example, because this is a practical situation. For example, here y x variable is education level, y is the income. So, for example, suppose you consider a person whose education level is say 5 years or 6 years, and then for that person we cannot talk about if you increase his level by 1 year, what will happen to his, talking about that is not meaningful, right? What is we can explain here is if you consider a group of people whose education level is 5, if you consider another group of people whose education level is 6, then there will be a difference between the average income. So that amount will be given by the slope. So it's not increasing the education level of those who are already 5. If you increase them to 6, if you ask them to go to school another year, there will income. We cannot say like that. Right? But here we can say that if you increase x by 1 minute, because in mathematics we change the x value, right? We assign the value, and then we can say if you increase x. So that is therefore there is a difference between the interpretations like that. So in the regression we can say the slope is giving you the average change in y if you consider x values 1 unit apart, right? If you increase, in that sense if you increase, right? Not the practically increasing. Right? That practically increasing might be maybe meaningful. Yeah, so in this example actually we have observational study, right? But if you have a practical or experimental study, then it's meaningful to talk about increasing x. We can practically increase, right? We had an example where this weight, you put a weight to this string and see how much it is stretching and so on. So you can do it. You can increase for the same experiment. In that case, it's meaningful to talk about how much change will be in y on average if you increase x by 1 unit, for example. But if you're talking about observational study and then regression relation to that, that kind of interpretation is not meaningful. And then in a mathematical equation straight line, what does A mean? Interceptor means
when x is 0.
yeah, that's how you usually interpret it, right? What is the value of y when it is equal to 0? But again, in regression, it's not meaningful to talk about like that most of the times, right? Because when you say what is the income if the education level is 0, it's going to be negative something, and that's not going to be meaningful also. Right. On the other hand, this regression was fitted when we're fitting this one x equal to 0 rate, those values are not in our data set, right? So that's therefore we have already mentioned that when you interpret something, we should be careful about interpreting the y values for the x values that is in the data set. Right? So we don't know what happens if x equals 0 and whether it is explained by this model or not. So therefore, x equal to 0 probably is not a meaningful thing to talk about in this case, right? Because the minimum value that we can talk about in this model is the minimum value of x in the data, right? So in that case, we may not be able to give a practical, physical meaning to the intercept. Right? There can be situations where x equal to 0 is either in the data set or maybe it's more practically meaningful. In that case, for example, we look at the other one. When we look at that string, before we adding any weight to it, so that is the situation when there is no x equal to 0 situation or m equal to 0, whatever the weight that you are adding. So in that case it has a meaning, but in this case it doesn't have a meaning, and that means the slope, intercept doesn't have a meaning. But of course you have to have a value, but it doesn't have a practical meaning in that case. Right. So once you have the equation, of course you can predict the average y value for a given x within the range of x's in the data set. So this is what explains what I just explained. So when you are interpreting the slope, you have to be careful, especially using the words, not like in mathematics. You say that is the change in average y, average change in y associated with increase of x. When you say associated, it doesn't mean really physically changing, right? So that's the difference between two x values, 1 unit apart. Right. So these are the book. So we look at this example activity like this. Yeah, I just wanted to show you that, okay, if you consider, I told you that there are two regression lines, right? Y versus x and x versus y, and they are two different things. And you can actually now, because you know how to get the equation, you can actually find out the equation and realize that the equations are actually different. Right? Earlier we were just talking about slope and how much change in y and so on. Now we know how to get the equation. So therefore I ask you to, as an activity, I will assign that for you to check. Right? You will see that the two equations are different. Right? I have the answer here, but okay. So now I'd like actually to talk a little bit about mathematics. Even though this part is not mathematically explained in the book, I will look at it mathematically a little bit. So what is this really, the method is method of least squares. Still we got the equation beating around the bush, not directly, right? Assuming that we're knowing, accepting that fact that change in 1 unit of x will change y by r times standard deviation. So you use that fact to get the equation. But what we are really doing here is, you see, when you are using the least square method, so we have, we assume that we have a data set which has roughly a ball shape. So that's where we assume that the variability of y for different x is roughly the same. Right? So you will have different observations. So what you want is to find out a line that goes through this scatter, so that when you use that line to predict y values, overall error will be as small as possible. That is the criteria that we consider in least square method. Right? You can draw so many number of lines through these things. Right? So if you consider, for example, one particular line, let's consider this line. Suppose your data are something like this. So for a given x, this x, actual y value is this. If you use this particular line, suppose that is, say, y hat is equal to some a plus bx, where we don't know a and b yet. So there is a y value, observed value. So let me say this xi and yi, ith observation. So in that case, yi hat will be this amount. Now that will be equal to, if that is coming from that line, that is going to be a plus b xi, yi hat. So this is the prediction error in that case for that particular observation. Right? So you have xi, yi point for that particular observation, that is the prediction error. And similarly, if you consider another point, there is a prediction error. Right? So in the least square method, the criteria that we look at is try to find out the line out of all possible lines, try to find out the line so that the total error, total prediction error will be as small as possible. But when you consider the total error, there is a technical problem, because this error, for example, is about negative value. These errors are positive values, right? So it's possible that total error will be cancelled out. So therefore, directly using the total error is not a good criteria, because it's not going to give you a good line, because even for a bad line, total error can be very close to zero because of cancelling out. So one thing else you can do is look at, instead of looking at the actual errors as what you asked in the previous question, you can look at the absolute error if you want. Right? So probably you can look at the total absolute error. In that case, error is going to be yi minus yi hat. So this is the actual error. So we can look at, for example, yi minus y1 hat absolute value plus y2 minus y2 hat absolute value, and so on, the total, right? And then look at the line which gives you the total absolute error to be minimum. That's a good method, but again, as I explained in the previous class, it is not what we do in practice, because mathematically it is going to be a little bit difficult. Right? And the other thing is that people have found out that the line comes from using this criteria. If you minimize this criteria, the line comes from that is something called unstable. That means even if you change 1 or 2 points, then the line changes by a very much. Right? So that's not a good thing, because our line has to be kind of stable. Even if there is a small change in x and y, the line should not be changing that much. Slope and intercept should not change that much. Right? But what happens if you use this criteria? If you minimize the sum of absolute errors, you can get a line, you can find out suitable a and b values, but then that line, people have found out to be kind of unstable. So therefore, what we actually do here is consider the sum of squared errors. That is y1 minus y1 hat square plus y2 minus y2 hat square, and so on. If you have n observations, yn minus yn hat square. So this is the criteria, that is the quantity that we look at, and we call it sum of squares of errors. Sum of squares of errors. So we can write down now, we want to find out suitable a and b. Like what is the most suitable slope and what is the most suitable intercept. So we have to get a and b into the equation. So if you assume a particular line with unknown a and b, you can write down this as y1 minus then a plus b xi square plus y, in this case x1 here, y1 x1, and then y2 minus a plus b x2 square. So like that, yn minus a plus b xn square. So that is the sum of squares of errors. So you can see that that is a function of a and b. It's a function of a and b. Now we can find out what are the suitable values for a and b, so that this quantity will be minimum. So we have the observations, we know y1, we know x1. So the only thing in this expression which is unknown is going to be a and b. So it's a mathematical function with, for example, 2 unknown quantities. Right? You can change, mathematically we can change, we can give different a values and different b values, and then SSE will be different for each case. Right? So what are the values a and b that gives you the minimum of this quantity? Right? So how do you find out that those two values? You have to get, there are two unknowns of course, therefore you need two equations. So what you do is you partially differentiate this thing with respect to a and equate to 0, because you are looking at a minimum. At the minimum or maximum or cycle point, you know the first derivative is 0. Right? So what you do is you take the first derivative of SSE with respect to a So you have an equation, you equate it to 0. And then you take the derivative SSE with respect to B and equate to 0. And solve these two. Right? Solve these two. Then you get a certain value for A and certain value for B. But that is what that tells you is that at that point SSE will have either a maximum or a minimum or a saddle point. We don't know still whether it's a minimum, definitely. Right? It can have at that point particular AB point. SSE can have a maximum or a minimum or a saddle point. So then usually we have to check for the second derivative condition, right? Second derivative condition to check whether actually this is going to be a minimum. Theoretically we know that, but of course you have to check usually in a proof you have to check, right? The second derivative condition, and you can show that at that point actually SSE will be minimum, right? So therefore those AB values that you get by solving these two equations are called the least squares estimates. Least squares estimates of A and B. Right? So the line, then there will be a value for A, there will be a value for B. And when you put those two values, we get y hat. For example, A is equal to 5 maybe, B is equal to 2 or whatever you are getting from here. So that line that you get is called least squares regression line. So that is actually the line that would give you the sum of squares of errors minimum sum of squares of errors. So that's what this particular method is. Mathematically, that's how you do it. Your book doesn't contain that part, but you can understand that. That's why I included that. Right. I mean, explain. I have not even put it in the note because it is not in the book. But this is what we usually do. Get the sum of squares in terms of A and B, assuming a particular line with unknown A and B, right? And then find out the value of A and B so that this quantity is minimum. So if you look at this particular example that somebody has done by adding some weights to a string and seeing how much it stretches, so starting with some length of a string and then add different weights. They have measured how much the total weight after adding that. So they have got some data like this. So when they plot the data, of course they don't, they are very close to a straight line. Of course there is a physical relationship, actual physical relationship between this weight and the length. But because of some maybe measurement errors and so on, random errors, they are not going to be exactly on the line in these kind of practical situations. So that was the picture that they got. So they use this particular method to find out A and B using the least squares method, least squares estimates. Right. So in the book actually they have not done it, they have just mentioned that when they use the least square method, they got some two values for M and M is the slope according to their notation, B is the intercept. So they got something like this. Actually what I did was, in order to explain this thing without, I thought maybe I will probably not talk about that, but practically just to explain what it means, I looked at different values for M and B, for example, few values. What I did was I changed this A and B according to this equation, or maybe it's according to the books one, it is like B plus mx. So by changing B and M slightly, I looked at several possible lines. Right. So these are different possible lines. I have about 4 lines here. So what I did was just calculate this quantity, sum of squares of errors for each line. If I consider this line, for example, I can find out the difference between y and the point on the line. So I have that error, and therefore I can find out the sum of squares of errors for that particular line. And then I can find out the sum of squares of errors for this blue line and so on. So when I did that, I got this table of root. Actually, what I have here is the root mean square. So if you take the square root of that, that is the one. Right. If you minimize the sum of squares of errors, of course, root mean square will also be minimized. So for different slopes, I have just put some slopes very close values, because there is no point of drawing points even like this. There is no point. No? So I just considered several possible values, and then you can see that out of these values, what is the minimum root mean square? Yeah, this one. Right. So actually, this is not the method, because we don't physically do this. Right. The method is mathematical, but I just wanted to explain what is actually happening. So out of at least these 5 lines, you can see that these two values gives you the smallest root mean square. Right. So if you actually mathematically did it, these are the values that you the actual values that you get are actually very close to this, right? Like 0.05, and then this is like 439 something, right? If you actually mathematically get it, actually square values are very close to that too, right? I just wanted to explain what we really are doing mathematically here, because that's not in this part is not in the book. But usually in the university, when you are learning regression, this is where we start. Right? We just talk about the least square and mathematically explain how to do it. Right? This book is not for mathematical students, therefore they are not even to talk about the mathematical equations. But that is what the least squares method is. So when you do that, of course you get this equation, right? This the same equation comes when you apply the least square method. So when you apply the least square method, you get the same equation. Right? So that means your b value is going to be this value. You will get this value for your b when you apply this method. And then your a value, sorry, this intercept will be given by this equation. That's where they are actually coming. So actually this b slope is coming like this from that mathematical equation. Once you get that, of course you break it down and see that value is actually r times sd of y divided by sd of x. So therefore you can give an interpretation like that. If you increase x by 1 standard deviation of x, y on average changes by r times sd of y in the least square method. ඒ විදිහටයි ඒක ඇවිල්ලා තියෙන්නේ. ඒ කියන්නේ මැතමැටිකලි මේ විදිහට ලබා ගත්තට පස්සේ b කියන එක අපිට පේනවා ඇත්තටම b කියන එකේ මේ ආකාරයේ ෆෝමියුලා එකක් තමයි තියෙන්නේ කියලා. එතකොට ඒ විදිහට ඉන්ටර්ප්‍රිට් කරලා කලින්ම ඔක මැතමැටිකලි කරනකොට ওই විදිහට එන්නේ නැහැ. එන්නේ මේ විදිහට slope is something like this xi minus x bar yi minus y bar divided by square root xi minus x bar square times yi minus y bar times ඊට පස්සේ xi minus x bar square root of ඔය වගේ එකක් එන්නේ. දැන් තව ඉංග්‍රීසි බෙදලා මොකක්ද තියෙනවා. ඔය වගේ ප්‍රකාශනයක් තමයි ස්ලෝප් එකට එන්නේ. ඒතකොට ඒක කඩලා බලමු අපිට වෙනවා. මෙතන r වලට තියෙන ෆෝමියුලා එකේ කැලලක් තියෙනවා. ඊට පස්සේ ඒක වරක් sd of sdy කියන ෆෝමියුලා තියෙන එකකින් එනවා sd of x කැලලක් එනවා sd of y කැලලක් එනවා. උඩ කැලලක් කපලා එනවා. උතන y minus y bar. ඒන සූත්‍රයේ අපිට කඩලා බලපුවම මේ ආකාරයකට ගන්න පුළුවන්. ඒතකොට ඊට පස්සේ ඒක ඒ විදිහට ඉන්ටර්ප්‍රිට් කරලා තමයි අර විදිහට එක්ස්ප්ලেইন කරන්නේ. The formula you're getting is something like this. Okay. Okay, then after that book actually discusses about you have to think about when you're fitting a regression line whether that regression line is actually a meaningful thing or not. Uh, One thing is actually you have to have first of all a straight line relationship to fit a straight line equation, right? So therefore looking at the graph is very important. That is one point. Another point is you have to think about the practicality of it also. To explain about that, they have looked at a relationship between the area of some rectangles and what you call circumference, right? The
Perimeter.
perimeter, yes. Circumference is for the circle, right? Yeah, perimeter. Yeah, so they have looked at the relationship between the area and the perimeter, and they have considered all these pictures, these rectangles actually. For these rectangles, they show that there is a very close straight line relationship between the area and the perimeter. So therefore mathematically we can fit a line, right? So when they looked at the area and the perimeter, this was the picture. So you can see that they are very increasing with the area is increasing with the perimeter, very close to a straight line. So you can mathematically fit a line and get a line, but of course you have to think whether that kind of regression line is practically meaningful. In this case, the correlation was very high too. But the book says, for example, this is not a practically meaningful thing to do because now this kind of thing, somebody might do this kind of thing to find out the relationship between area and the perimeter if they didn't know that area is actually equal to the product of height and weight, height and the length. Otherwise, nobody will do this kind of regression. Right? So, but if the objective was to find out the relationship between the area and the perimeter, that's not a meaningful thing to do because we know now the area is a function of height and length and the width, and the perimeter is also a function of length and width. So there's no point of looking at the relationship between these two ones. Your y is a function of these two variables and x is also a function of those two variables, right? But mathematically, of course, at least for these particular rectangles, you can say that there is a relationship. Right? That is not going to be valid for all the rectangles because we have not particularly looked at, for example, this kind of rectangles, right? It's not included there, right? So if you look at these ones, most of them are having roughly the same length and width, right? So for that kind of relation, ones maybe this regression is meaningful, and even you may be able to predict once you know the perimeter, but it's not valid for all the rectangles. Right. Actually, that's all that is in the book regarding regression. So you have to be careful, especially in interpreting in the regression. Once you get an equation, there will be a relationship between y and x. Most of the times, especially when you have observational data, you have to be careful not to interpret that as a causation. Y is not necessarily causing x. For example, you cannot say if you increase x by 1 unit, y will change on average by this. You cannot interpret it in that way. So you have to be careful in the interpreting. You can do that if you are using the data came from a particular experimental study. Right? Otherwise, but usually we use regression mostly for observational studies. In that kind of situations, interpreting you have to when you are interpreting you have to be careful. Right. Okay, I think that's enough for regression also for But remember, this is simple linear regression, right? But this is not the most useful regression, right? You use the regression mostly when you want to find out the model, you want to model the relationship between one y and several x's. Right? So that's where the regression method is more suitable. In that kind of situations, you cannot even do mathematics like this. Usually you have to use something called a matrix method, right? Because in that case, you will have a vector of y values, y1, y2 and so on up to maybe yn. But there will be several x's, x1, x2, x3 and so on. For each x1, x2, x3 you will have data. So you will be dealing with a matrix of x values, not a column of x values in that case. So in this case, still you can get an expression for the sum of squares of errors, but they will be in matrix notation, and then this differentiation will be again in matrix notation. So finally you will get, so your model will be still something like this: y hat is equal to some x times beta, right? So y hat will be your vector, and this x is going to be this x here, and generally there will be a column of ones also, where this beta is going to be having, for example, b and m. It is a vector of two values. So this x and beta y hat, you can find out estimated value for beta, and it's going to be in the matrix notation. Beta hat is going to be x transpose x, x transpose x inverse x transpose y. So if you say y hat is equal to x times beta hat, then beta hat is going to be given by this equation when you look at multiple linear regression. So that's what actually more practical thing. And then there will be, in this kind of situation, simple linear regression and multiple linear regression. Once you fit the model, you are interested in doing inference, right? You can get an estimate, you can get a fitted value for a y or the average y for a given x. So that's it will give you only the point estimate, single value. But then there is a question: how accurate is that value? Right? How confident can you be about that predicted value? Right? So therefore, we have to give some measure of accuracy about for that value that we talked about. Root mean square error is the value. Right? In addition to that, we can also give a confidence interval for the predicted value. We can say the predicted value, the y on average for this x, y will be within this interval, and we are 95% sure about it, and so on. So that kind of things called inference. In order to get that kind of inference, we need more assumptions. Right? One assumption that I explained earlier is that we have to assume that for a given x, possible y values have a normal distribution. So we have to have some distributional assumptions to get that kind of confidence intervals. Right? The same applies to multiple linear regression also. So simple linear regression and multiple linear regression, we assume that y's for a given x are normal. Right? But there are situations where that assumption is not suitable. There can be some other type of data, for example, something called Poisson data, binomial data, and so on. So in that kind of situation, still if you want to find out the relationship between y and x's, we use something called generalized linear models. Right? So there are so many branches of regression, and there can be non-linear relationship. Right? And there is also something called without this normality or some Poisson or some kind of distribution assumption, also it's possible to fit models. So these are called non-parametric regression models. There are so many branches. But this is just the surface, simple linear regression. Okay. Then shall we go to the next chapter? Or do you want a break? I don't know.
We have turned on this.
Ah, yes, you are feeling the heat now. So the next several chapters is about probability actually. In this case, I am going to deviate somewhat from the book because the book is so elementary. I don't think that is very much interesting to talk about exactly following the book. So I have changed a little bit, but still I have included the ideas in the book. But my notes will be somewhat different from books what we have in the book. So in the book, of course, I have used the same titles, topics and so on. But the content I have tried to be a little bit more mathematical than the book. So before we talk about the probability, we know that we always, in real life, we use different words to have roughly the same meaning, right? The probability is a technical word mostly. But people talk about chance, likelihood, possibility, right? What is the chance of happening something? What is the possibility of happening something? What is the likelihood of happening something, right? So that kind of questions are always arising in real life, right? So for example, what is the chance of getting a job after you finish your, or generally what is the chance of getting a job for an undergraduate in a certain field, right? What is the chance of meeting somebody, right? Yeah, according to your preferences when you are in the university, for example. What is the chance of rain, right? For farmers, for example, it may be very important. If he is going to say sow paddy, so he has to know what is the chance of rain in next few days because he has to decide. අපි දන්නවා පෙහෙන්ට දාලා ඒක මෙවුනට පස්සේ ඉතින් ඒක දවස් කිහිපයක් මෙහා ඉඳලා plan කරගන්න ඕනේ. ඒක එතකොට right you have to plan what will happen in few days. So that kind of questions are in everybody's mind always. Right? But of course, sometimes it's enough for us to just talk about, okay, there's a very high chance, or maybe medium chance, or very low chance of happening something. If you just explain it in that kind of words, maybe enough for something, most of the times. Right? But there are situations where that kind of explanations are not enough. Probably you need some mathematical value, especially if you want to compare the possibilities of two events, right? Or maybe, okay, if you are considering, if you are planning to organize certain, say for example, cricket match, right? You have several options for places, right? So you think, what is the chance of having rain in this place during this period of time? What is the chance of having rain in the other place during the same period of time? Right? So then it is not probably enough to say, okay, there is a medium chance or high chance and so on. You may have want to be able to compare mathematically. Right? So that is where the numerical value is important. Right? So similarly, in the past also, there was a question regarding, whether it's possible to numerically measure the chance of happening something. Right? So always when you talk about chance, the possibility and likelihood, actually we talk about those things with some event, right? So always, what is the chance of some event? What is the possibility of an event? What is the likelihood of an event? Right? So always these words come with an event. So if you want to compare or get a mathematical value, again, that is what is the mathematical possibility, what is the mathematical chance of that event. So that requirement arose long time ago. Especially somebody wanted to compare the chances of winning in some games, especially what you call gambling. Right. So this always comes with some bad things, the ideas, but of course, right. So they wanted to see, right, what is the which game has higher chance of winning. Right. There are different types of gambling games, so that's where the mathematical idea usually was important at the beginning, as far as I know at the moment, right? So this question was in the mind of some gamblers, and they put this question to some mathematicians at that time, and they therefore developed the idea of probability, right? That is where the idea of probability came, right? The way to get some mathematical value for the idea of chance. So that's what I have put it in this introduction here. I have put some examples of places where you want to be able to compare mathematically the chances, so you can read the note. So that's where we actually, this idea came, right? Many of the early questions about chance arose from games of chance, such as card games, lotteries, and so on. So one person called Abraham D. Mouviri or something, a French person, I think, mathematician, was the one who had this idea. So he gave this idea to some other mathematicians. They were the one who did actually. This is the mathematician mainly looked at this idea about the probability. The person who was interested in was not a mathematician, he was just a gambler. So he put the problem into this person, and he thought about it and developed some doctrine of chances, and even wrote a book by that name. Right. So therefore, it is, you can see that we always talk about now, we are not going to use the word chance and so on, they are just layman words. So we need a technical quantity to measure the possibility or the chance or the likelihood of some events, right? So therefore, in order to talk about the probability, in order to talk about this mathematical concept, because we talk about the probability of events, we first have to define an event also mathematically. It's important to define an event mathematically, then only we can talk about the possibility of the event mathematically. So this part is not like this in the book, but I usually when you teach in the university, this is how we teach it. Right? So in order to define event, first of all, we need some other technical terms. Right? We have to use those technical terms to define an event mathematically. So usually the word we start with is the word experiment. So we need a new word, technical word, to explain events. So one word we use is experiment. Right? Usually when in the layman meaning, when you say or when you hear the word experiment, we just think about some scientific experiment done in a lab, physics lab or chemistry lab. So anyway, in general, experiment means some thing that is scientifically done with some kind of control, right? You control several variables and observe something. What is the outcome and so on. But here in this class, when you talk about experiment, it's a little bit more general than a scientific experiment. We are going to use the word experiment for any action or a process of action, several actions, a series of actions, which gives you some observation, which gives you some outcome. Right? So therefore, the word here is a little bit more general. So even without a scientific experiment, we can use the word experiment here. That is any action or process or procedure that generates data or observations. So we will use that word experiment in that sense. And then more importantly, actually we will be use the word random experiment. So random experiment is a particular type of experiment with some particular properties. Right? If some experiment can be repeated again and again and again, approximately at this with the same conditions. Right? Practically, theoretically, we say a random experiment is an experiment which can be repeated under the same conditions. But practically, of course, it's not like that. We cannot have exactly the same conditions. So roughly in practical situations, even if the conditions under which we repeat this experiment is roughly the same, we consider them to be random experiment. And another condition is that before we carry out one experiment, we should not know exactly what the outcome would be. Right? There can be several possible outcomes, but we don't know which outcome is going to be the outcome in this particular experiment when you do that. So that's where the randomness comes. Right? So the outcome, we should know, probably most of the times we should know what are the possible outcomes. Our outcome, another word is outcome. Outcome is the result actually. Result of one experiment is called the outcome. So there can be several possible outcomes. So we don't know which of these is going to be the outcome in one particular experiment. So that is another condition. Right? So can be repeated, can be conducted under identical conditions, and then has to have a set of values, set of outcomes, but we don't know, the outcome should be uncertain. So if that is the situation, then that kind of experiment is called a random experiment. Right? So mostly we actually talk about probability of some events coming out of random experiments. Right? Of course, some people talk about the probability of some events coming from non-random experiments also, but in this class at least where we are talking about the probability coming out of random experiments. So here I have looked at few situations or few actions or processes where maybe data is generated. So we look at some examples and decide whether they are random experiments or not. Just take each situation here, each scenario, and see whether those conditions are matched here. For example, just take a very simple one, tossing a coin and observing whether it shows a head or tail. Is it a random experiment? Yeah, because we can toss the coin approximately the same time, the same condition, and of course we know that we are going to get a head or tail, but in a particular toss we don't know whether we are going, before toss we don't know whether we are going to get a head or tail. So that's a random experiment. Okay, this is another just experiment, a word or sentence, predicting whether a particular candidate will win a specific presidential election. Predicting whether somebody. No. Actually, predicting something is not an experiment. Predicting something is not an experiment. Right? So that is out of the situation. Prediction is something that we do after we fit a model or something, but it's not an experiment.
Because guessing will be
Guessing will be yes. Guessing, yeah, but that is again kind of prediction. But guessing, yeah, it's like tossing a coin, right? You toss a coin and then, but here predict. But can we? Yeah, there's an important thing. So if you consider a particular candidate, is it repeatable something? Right? It's not a repeatable thing, no. So you can guess once, right? It's not, you are not doing the same thing again and again and again. So in that sense, it's not an experiment, right? It's not So that's where actually, but still we can talk about the probability. For example, probability some particular person is winning. It's meaningful to talk about, but that is called subjective probability usually. What we are going to learn in this class is something called objective probability, frequentist approach. So that is why I said we are going to consider only random experiments. Inspecting a randomly selected product from a production line and observing whether it is defective or non-defective. Inspecting a randomly selected product, so we can get randomly selected products under the same conditions several, right? Observe one and then take another randomly one, observe under the same condition and so on. So therefore that is, we don't know whether it's going to be defective or not at the moment. So, but if you are going to record your outcome as such, you have to have a clearly defined set of outcomes. What are the possible outcomes? So, therefore, the outcome that you should be looking at must be defined, right? So, for example, inspecting a product, you can observe and get something else, for example, whether the color of that thing. Right? That is a different experiment. Right? Here, the experiment says, we are observing something and then recording, for example, whether it's defective or not. So therefore the set of possible outcome is defective, non-defective. Right? But we don't know whether something item is going to be defective or not. Right? And recording the number of customers arrive at a service counter during a randomly selected 10-minute period. So is that a random experiment? Yeah, we can pick the time period 10 minutes randomly. So within that, we can see how many people come. And again, within another 10-minute period, so we can repeat it, right? So we can look at the number of customers within that period also. Therefore, that can be considered as a random experiment. Measuring the height of a randomly selected person from a group. So that again, we are not measuring the same person, randomly selected person, so the person will be different person was in different experiments. So it can be repeated under the same condition. Under the same condition means you are maybe measuring with the same tape and so on. So that's what it means by under the same condition. Picking a ball from a box containing 2 black and 3 white balls. Picking a ball from a box containing 2 black balls and 3 white balls.
So when you say the outcomes, the set of outcomes you should know, but you don't know the exact way. But the thing is, with the height thing, you don't know the exact heights, and we only know the range.
No, in that case, what you mean by knowing the set means at least you know the heights are in a particular interval. So that you know, for example, in a certain, it cannot be 100 meters, right? It's going to be maybe, say, in feet, for example, 2 feet to 7 feet for Sri Lankan people. There's a reasonable expectation. So in that sense, right? Not exact. Because these outcomes can be continuous or discrete type, right? Especially when it's discrete, most of the practical situations we know what different ones. But if it is continuous set, you don't know exactly. You cannot say because there are millions of possible values. So it's in that sense, right? It's in a certain interval. Right? Here, picking a ball from a box containing 2 black and 3 white balls.
It doesn't say without looking.
Sorry?
It doesn't say without looking.
That's right. That's an important thing actually. It just say picking and it doesn't say what the outcome we are looking at. Outcomes are not defined in this sentence. Right. So if you say, for example, picking a ball from a box containing 2 black and 3 white balls and observing their colors, that is going to be. So when you observe, at least you have some outcome, right? Color, right? Observing the color, right? Or you can define picking a ball. If you are taking one ball, you are observing the color of that ball. Right? So that part has to be there for it to be an experiment. Otherwise, it's not just an activity. It's not an experiment in our sense. It's not a random experiment. Right? You have to. That's what we say. It has to have well-defined outcome. Outcome has to be explained. Right? Counting the number of defective items in a random sample of 10 products. Counting the number of defective items in a random sample of 10 products. So that's going to be a random experiment because 10 products can be selected again and again and again from a batch. So in each we can count always. So there is a possible outcome, right? So possible outcome can be in that case 0, 1, 2, 3 up to 10 any value. Recording the outcome of a specific sports final. Recording the outcome of a sports final. For example, you got World Cup 2025 or 20 whatever. Is that a random experiment? Why not? You cannot repeat it. You are looking at a particular one, so that cannot be repeated. Yeah, that's not a random. But still, people can talk about the probability of that. What is the probability that Sri Lanka will win a certain World Cup and so on? You can cricketers, so sports. Some people can talk about it, and some people will give their ideas, but that is going to be subjective probability. Different people will have different probabilities. But what we are going to talk about is here, once you calculate the probability of an event, no matter what person calculates it, you get the same value. So that kind of objective probability is what we are interested in. Right. So to continue the terminologies, now random experiment is one important word. So outcome is actually the result of any single experiment, that is the outcome. And then the set of all possible outcomes. Right? If you repeat, now we are looking at possibility of repeating random experiments. Random experiments are possible to repeat. So if you repeat this experiment again and again and again, different outcomes will come. So what is the set of all possible outcomes? You can write down it as a set. So that set is called the sample space. Sample space. Right. So this word sample space sometimes is confused with the sample that you take. Those are two different things. If you, for example, if you take a sample of products from a batch, that is a sample. නියඳියක්. මෙතන නියඳිය අවකාශය කියලා කියන්නේ එතන මම දන්නේ sample කතාව ආවේ කියලා. That's the word they have been using it. So that's not the same as the sample. Right? These are a set of possible values that is possible to get if you repeat the experiment. So event is the important word that we are looking at because we wanted to mathematically define an event. So in the elementary level, we define event to be any subset. Any subset of a sample space is called an event. That is in the elementary level, but there's a mathematical problem here sometimes if you define any subset. So therefore in a little bit higher level there is something called sigma algebra. I don't know whether you have learned about that. Sigma algebra is, for example, if you have a sample space, there can be a collection of subsets where for some subsets we cannot call it an event because we cannot calculate the probability of that event according to the definition of the probability. Remember that we are going to now talk about mathematically the word probability. So in that definition there will be some mathematical properties that has to be satisfied by the word probability. That function, we are going to define a function, right? So when you look at a sample space, especially when the sample space is continuous, right, there can be some peculiar sets. Mathematicians come up with some peculiar sets for which we cannot talk about probabilities. Right? So therefore, in the advanced level of definitions, we define an event to be a subset of a certain thing called sigma algebra, but I am not going to because you have not learned measure theory. We need something called measure theory for that. So for the moment, it's enough for us to say that any subset, right? In most of the practical situations, that definition is enough. Any subset of S is called an event. Sometimes any subset may not be interested to us. Only some of the subsets will be interested to us, but any subset of a sample space is mathematically called an event. Therefore, generally we can talk about the probability of having any subset, getting any subset. Right. So usually when you are writing down the probability and so on, we will be using a notation because otherwise we have to write down so many words to explain an event. So, and everywhere we calculate the probability that has to be written. So therefore, in order to avoid that, usually you will define the event at one place using a notation, and then you will use that notation later on to reduce the amount of work. Otherwise, there is no need. Especially, for example, book doesn't use any notation; it always uses words. So therefore, an event is actually a set. A set can contain, can contain maybe no what you call elements. So that is called null set, right? Empty set. Empty set is usually denoted like this, or denoted like this. Right? Empty set is a particular set mathematically, but don't write like this. That is not the empty set. This one is inside that. It's not empty, right? So either this or this is the notation for empty set, and also there can be maybe only one element or more than one element in a set. Right? If there is only one element in a set, that kind of event now for us it's an event is called a simple event. This one is called the null event, and if there are more than one element in the set, that kind of events are called compound events. Right. Just for you to know, because when you read the books, for example, you might come out of these words, simple event and compound. These are not in the book, in your book. Okay, let's look at just a very simple example. This might be boring, but let's look at them anyway. Let's consider an event. A die is rolled. Suppose this die has 6 sides. We are not going to talk about whether it's something called fair die or not. But suppose it has 6 sides, and each side has a number 1, 2, 3 up to 6. So assume that. So let's say the event of getting a number faced up is 3. So that is one possible event. That is the event of getting 3 in the faced up die. Right. So if that is the event, then we can probably denote it by A, and then event has only 3. The sample space in this case what? The sample space is 1, 2, 3, 4, 5, 6. That is the sample space. Usually we use S, or some people use this omega to denote sample space, but I use S here. So S is reserved for the sample space, and then the other letters can be used for the events. So if you look at the event of getting an even number, and let's call it B, and then in that case that is a set again, 2 or 4 or 6. Right? So in particular experiment, for example, if you get this number, then we say event B has occurred. Event B has occurred. Right? You don't have to get all 3 numbers to say that event B has occurred. Right? So this is one possibility of happening event B. There is another possibility, another way of happening event B. There is another way of happening the same event. Right? So if you get any of those in a particular experiment, in one experiment, then you say B has happened. And see, the number of faced up is less than 5. So these are the numbers less than 5 possible numbers. Right? You already know, usually in a simple settings, we use something called the Venn diagram to show these different sets or different events. So for example, for this particular situation, we can use a Venn diagram like this. Right? So this Venn diagram, actually, Venn is the person who invented this kind of pictures. It's a name of a person. Venn diagram is called. So you don't have to have, most of the books usually use circles, but you don't have to have circles. You can have any shape show the set. Right. So this will be the picture, the real diagram, for example, for this particular example. We will talk about the probability of these things little later. Right. For the moment, we are going to only look at events. So can you read this question and write down the two events mentioned here? In addition to that, you can write down the sample space also. So write down the sample space and the two events. A box contains one ticket with number 6, two tickets with number 5, three tickets with number 4, and so on. A ticket is taken randomly from the box, and then you have to say you observe the value on the ticket. That part is not mentioned here. And then event A is the number received is an even number. B, the number received is less than 5. So what will be the sample space?
1, 2, 3, 4, 5.
Yeah. Yeah, when you write down a set, you know, even though now there are 6 box contains one ticket with 6 and several, for example, 2 tickets with 5, you don't write down 5 twice, right? You write down the same one number only once. So therefore, still the same sample space as the previous one. The sample space that you had when you consider rolling a die. So A is the number received is even, is 2, 4, 6. Right. So B, the set, the number received less than 5 is 1, 2, 3, 4. So the sets are actually the same as the previous example. Right. Just rolling a die, just 1, 2, 3, 4, 5, 6. But the scenarios are different. So therefore, the probabilities has to be different because the probability of A in that situation may not be the same as probability of B in this situation. So, so we'll talk about those things a little later. Okay, let's look at this one. In both cases here, the sample spaces are finite. There are only finite number of outcomes, and the sample spaces are discrete also. So there are differences. Sometimes your sample space can be discrete, sometimes it can be continuous. When it is discrete, the number of outcomes can be finite or it can be infinite. There can be discrete, but still there are large number of, we don't know the so n, so infinite. So like that there are differences. Okay, let's look at this one. The box contains 3 white balls and 2 black balls. Right. A ball is taken randomly. A is the event getting a black ball. So here, okay, write down the sample space and then write down the event A, for example. How do you write down the sample space? Only look at this one because these are different ones. Getting a black ball, right? So that the event actually is related to observing the color, right? Observing the color. So how can you write down sample space? there's no particular unique way. Different people will write down in different ways actually. One way is to just to observe the color, right? So in that case, it can be, for example, we denote black by B and white by. Okay, let me use simple letters because I use capital letters to write the events. I will probably use simple letters to denote the elements. So black, white. That is one possible way to write down the sample space. Black gold, or it can be black or white. Any other way to write down the sample space?
Just like black and white. Just like black and white.
You know, in that case, we say black will be not in. But some might assume, for example, right, even though it's not mentioned here, there are 3 black white balls and 2 black balls. So maybe if somebody wants to consider these balls individually. So in that case, one might say B1, B2, B3, differentiating them. Right? Yeah, black, but 3 balls. Right? And then white 1, white 2. That is another possible way to write down. So if you write down sample space like this, then this event will be just 1B, right? If you write down the sample space like this, then that the same event will be B1, B2, B3. Okay. So depending on how you look at it, can be different the way that you write down the event. Okay, let's look at this one. So suppose you are taking 3 balls randomly. I want to talk about the event B, getting a black ball. So still the color is the important one. So if you write down sample space like this, probably it's difficult to write down that event as a subset of this, getting 3 balls. But here you have all 5 balls here, therefore we can easily write down that event. So depending on what event you want to look at also, the way that you should write down the sample space may be different. Right. So if you consider this sample space, then how do you write down event B? Getting a black ball.
B1, W1, W2.
Yeah. So getting 3 balls, right? So outcome will have 3 things in it, but one of these has to be black. Getting a black ball, right? So one might ask, when you say getting a black ball, getting 2 black balls, is it included or not? That's also a question, right? So therefore, probably this event is not very clear enough. Somebody will have to say getting 1 black ball if you really want. Getting 2 black balls is a different event. Or getting at least 1 black ball. So if you say just let me change getting 1 black ball. So in that case, for example, B1, W1, W2 is one possible outcome. Right? Outcome contains all 3. Right? And similarly, B2, W1, W2, and so on. So there can be like that. So you can write down the outcomes without considering the order. That is one way to write down. You don't consider, as far as there is one B here, whether it's the middle one or the last one doesn't matter, the same outcome, because it will have the same outcome.
So the sample space should be B1, B2 and W1, W2, W3, because there are
Sorry?
3 white balls.
I didn't understand.
There are 3 white balls. You have to mix the sample
Okay.
space.
3 white balls. Yes. 2 black balls. Right. So like that you can write down all the possibilities. Or if you want, you can even consider the order. In that case, there will be 2 more here. Right? W1 can be here, V1 next one, and like that. So depending on how you consider it, your sample space can be different. Right? So there is no one particular unique way of writing down it. Let's look at the second one, getting two black balls. It says exactly two black balls, so you can again look at that. Now, if you want to look at that thing here, getting two black balls, probably you can define your sample space in a different way also. Somebody might write down the sample space in a different way. Right. Here we have written down the sample space by considering, observing the color. Observing the color. Right. One might define the experiment as taking 3 balls randomly and counting the number of black balls in the sample. That is another way to look at, define your experiment. If you define your experiment like that, this particular event can be written using that sample space. Right? If you define the experiment as getting 3 balls randomly and counting the number of black balls in the sample, in that case sample space will be, sample can have, you have taken 3 balls now, so number of black balls can be 0, all 3 can be white, so therefore 0 is a possibility, number of black balls, right? 1 is a possibility, 2 is a possibility. So depending on how you define your experiment, right? Depending on how you explain what you observe, your sample space can be like that. If you write down your sample space like this event can be written as a subset of that. Right? So you can write down C as just 2. So you can see that there is no particular unique way of writing down the sample space. Right? You have to first of all look at what is the event of interest. Right? And you should be able to write down that event as a subset of some sample space. අපිට වැදගත් වෙන්නේ අර definition එක දින පැත්ත නෙවෙයි. definition එකේදී කියන්නේ in the definition we say any subset of a sample space of a given sample space is an event. හැබැයි when you solve a problem we know the event, right? So we want to be able to write down our event as a subset of some sample space, right? As a subset of some sample space, then we can talk about the probability of that event. එතකොට එතනදී අපි event එක දන්නවා මෙන්න මේ event එකයි අපිට වැදගත් වෙන්නේ. We know what is the event of interest, so we check whether we can write down that event as some subset of some sample space. So we define our event in that case. මෙතනදී මම අනිත් පැත්තට event එක දීලා වරින් මොකක් හරි experiment එක දීලා කරගෙන කියනවා මේක මේ event එක කියන්නේ. නමුත් අපිට අවශ්‍ය වෙන්නේ අනිත් පැත්තට. event එක අපි දන්නවා. We know the event, we want to find out the probability. So we want to be able to write down that as a subset of a suitable sample space. So experiment එකේ මොකද්ද අපි observe කරන්නේ, ගණන් කරනවාද, කලර් එක බලනවාද කියන එක අපි තමයි define කරන්නේ. So according to that we can write down the sample space and then write down our event as a subset of that. So if you look at the number D, for example, the number of white balls in the samples is 2. So ඒකත් අරගෙම අපිට පොත ගන්න පුළුවන් වුණා. Number of white balls 2 කියන්නේ black balls එන එකයි කියන්නේ. එහෙනම් අර sample space එකේම මේකත් කියන්න පුළුවන්. Right. Right. So let's look at now all these previous ones actually the sample space was kind of discrete. The number of outcomes was finite. So these are a different one. In a production process, milk powder is filled into bags. The bag is said to be non-conforming if its weight is less than some value or greater than some other value. Otherwise it is said to be conforming. So there are 2 types of bags, conforming or non-conforming. The quality inspector has measured the weight of 500 randomly selected bags. The frequency table is given here according to their weights. So again we might want to find out some probabilities, but at the moment we are looking at the events only. a bag is taken randomly from the process. A is the event that the bag is non-conforming bag. So how can we define? For example, suppose I want to find out the probability. I am interested in what is the probability that a bag is non-conforming if you randomly select a bag. So I suppose that is the one that I want to find out, the probability. So the event of interest is that the bag is non-conforming. Right. We will see later on that if you write down in a particular way, it's not going to be helpful to you for you to find out the probability. Give me a second. Define the sample space as conforming and non-conforming, for example. Any bag is conforming or non-conforming. If you define the sample space like that, you can say A is equal to non-conforming. So this is the only one. That is the way to explain it. But of course later we will see that if you define it like that, it's not going to help you to find out the probability. Right. What are the other ways of defining the sample space? In that case you can take the sample space or what you observe here. Here in this case you observe whether bag is conforming or not. So in that case the outcome is C or N, conforming or non-conforming. Or you can say you observe the weight, actual weight as your observation. So in that case how do you write down the sample space? Sample space can be any real number, for example within this and this. According to the data we know only that all the data are between this and this number. So we can say it has a set of real numbers. For example, you can say x in R such that x is between 396 and 405.
Can we use interval?
Huh?
Can we use interval instead of a set?
Yeah, it's a set. It's a set of real numbers.
No, I mean as the sample space, can we use interval instead
Yeah,
of?
sample space is set of all possible outcomes. Sample space is the set of all possible. It's a set. So in this case, any real number is possible as a weight. Right? So here I say I define my experiment to be take a bag and measure the weight. So in that case, my outcome will be the weight. Right? So set of all possible outcomes for the weight is any real number in this region according to what we have observed.
Yes, sir. I mean by the close intervals and open.
එහෙමත් කියන්න පුළුවන්. ඒක මේක කියලා කියන්න පුළුවන්. නමුත් සෙට් එකක් අපි සාමාන්‍ය ලියන විදිහක් නෙමෙයි මේක. මේ විදිහට කියන්න පුළුවන් ප්‍රශ්නයක්. So in this case you can say for example closed interval with 396 and 405. That's possible. But I think they will make a question. How do you define event A?
396.
Yeah, so you can say that if you use this notation, you can say x less than that, O the other one, and with so that x is a real number such that x is less than or equal to whatever the given number, or x greater than or equal to that. එහෙම නැත්නම් කොහොමද ලියන්නේ පුළුවන් සෙට් එක. අර විදිහට ලිව්වොත් අපිට ලියන්න පුළුවන් ඉතින් මෙතනින් මේ මේ පැත්තේ ලෝගර් එකේ ඉඳලා අන්තර මේක ඊට පස්සේ යූනියන් එකක් දාලා ලියන්න. මම සෙට් නොටේෂන් සෙට් ඔපරේෂන් එකකින් ලියන්නේ set operation. Right. So the other one, 3 bags are taken randomly from the process. Event B is that one bag is non-conform. ඒක ලියන්න පුළුවන් මේ sample space එකට අනුව ලියන්න පුළුවන්. Right. Non-conforming and conforming that. ඕක ගන්නෝනේ මේ දැන් මේකේ 3 ගන්නවා නම් මෙන්න outcome තුනක් තියෙනවා. ඒක උදාහරණයක් විදිහට මෙහෙම වෙන්න පුළුවන් sample space. n වෙන්න පුළුවන්. තුනම non-conform. c වෙන්න පුළුවන්. ඒ වගේ අනිත් ඒකෙන් subset එකක් විදිහට යන්න පුළුවන්. One drag is not conforming. All the outcomes with one name. ඒ විදිහට තමයි ලියන්න වෙන්නේ sample spaces. මේ sample spaces මෙහෙම ලියන එක අපිට එච්චර ප්‍රයෝජනයක් නැහැ. එක අවස්ථාවකදී හැර. When we calculate the probabilities, writing down the events as a subset of a sample space is important only if we are going to use something called the classical method to calculate the probability. There are different methods to calculate probabilities of different events. One method is called the classical method. A classical method එක අපිට පාවිච්චි කරන්න පුළුවන් වෙන්නේ we can use the classical method to calculate the probability of some event under certain conditions. I will talk about those things later, but I will just mention it now because I just talked about that. The sample space, you first of all you should be able to write down your event as a subset of some sample space. In your sample space, the number of outcomes should be finite. Infinite sample space එකක් නම් ඒතකොට මේ ක්‍රමය යොදන්න බෑ. The outcome event is up number of outcomes should be finite, and the other one is all the outcomes in the sample space should be equally likely. Each outcome should be equally likely. Then the probability of any subset we can find out using this method called classical method. අනිත් අවස්ථාවලදී මේ sample space ලියන එකේ ඇත්තට වැදගත්කමක් නැහැ ඇත්තට. කියන්න පුළුවන් වෙනවා මොකද අපි කියලා තියෙන ඕනම event එකක් is a subset of the sample space කියලා. So therefore we should be able to write down it. But mathematically when you are calculating the probability, it is important only when you can calculate the probability using the classical method, right? Otherwise we will have to use some other method called relative frequency method and also probability rules to calculate the probability. So we'll come to that little later. Right. So event is a subset of a sample space. Right? Any interested event we should be able to write down as a subset of some sample space. But of course, some events that we are interested in finding probability are not very easy events to write down. Sometimes there may be some complex events that we are interested in. Right? We may be able to write down a sample space and directly write down the events but the actual event that we are interested in may be a combination of some of these events. Right? So therefore, we need to sometimes combine events. That's where we need event operations. Right? You already know the union, intersection, and so on. So those are important to combine. Especially the thing is that there are some events for which we can calculate the probability directly. We can maybe observe the probability directly, not really observe, but we can easily calculate the probability of some events. There are some events of which we can calculate the probability easily. Right? Maybe using the observations that we have, we can calculate easily. But the actual event we are interested in may be a complex event. That maybe we should be able to, probably we can write down that complex event in terms of those simple events, not the word simple කිව්වොත් ඒක වැරදි නම් මම simple කියන ඉස්සර අර්ථයක් වань simple කියන්නේ එක outcome එකක් තියෙන events කියන. ඒත් simple කියන වචනේ දෙන්නට පාවිච්චි කරන්න බෑ. ඒකයි මම කිව්වේ easy කියන. Easy events. simple කියන එක දැන් වෙනම මේ reserve කරලා තියෙනවා. ඒක පාවිච්චි කරන්න බෑ. Simple event is an event which has only one outcome. ඒක මට පාවිච්චි කරන්න බෑ දැන් මට ඕන දේ කියන්නේ. මට ඕන දේ තමයි මේ සමහර ඉවෙන්ට්ස් තියෙනවා අපිට කෙලින්ම සම්භාවිතව හොයන්න පුළුවන්. ඊසි විදියට හොයන්න පුළුවන්. නමුත් අපිට අවශ්‍ය ඉවෙන්ට් එක ටිකක් කම්ප්ලෙක්ස් ඉවෙන්ට් එකක් වෙන්න පුළුවන්. ඒක කෙලින්ම හොයාගන්න බෑ. ඒකට අපිට කරන්න වෙනවා අර කම්ප්ලෙක්ස් ඉවෙන්ට් එක ඊසි ඉවෙන්ට්ස් වල කම්බිනේෂන් එකක් විදියට ලියා ගන්න. අන්න ඒ වෙලාවට තමයි අපිට අවශ්‍ය වෙන්නේ මේ ඉවෙන්ට් ඔපරේෂන්ස්. So you already know the event operations. Mainly there are three event operations: complement, and the intersection and the union, right? So what is the complement? Complement of a set is the set of outcomes which are not in that particular event but in S, right? So you can easily show it in Venn diagram, right? If A is a set, then this outside A is A complement. So that's simple. And the next one is the intersection, right? Intersection of two events, or you can talk about intersection of more than two events, but in order to define, it's enough to talk about intersection of two events. So that is the set of events which are common to both events, A and B, common to both. That if you consider three events, then that is the set of events common to all three events, so intersection. And then once you define the intersection, we can define this word, mutually exclusive events. If for two events, if there are no common elements, that means if the intersection is empty, right, then we say that those two events are mutually exclusive, right? Or we can say disjoint. So practically, if there are no common elements, that means those two events cannot happen at the same time. Then those two events cannot happen at the same time. For example, if you roll a dice, suppose you get a 2, right? So that means in that case, the event, even number has occurred. Let's consider another event, an odd number, having an odd number, right? So at the same time, when 2 has occurred, even number has occurred, that event has occurred, but odd number has not occurred, that cannot occur at the same time. Right? So that means getting an even number and getting an odd number are two mutually exclusive events. Right? At the same time, both cannot happen. Right. So you can Venn diagram, in a Venn diagram you can show it like this. Right? And then union is actually the collection of all the outcomes both in A and B. Right? So when you say, usually we say A, O, B in this case. For the union, the word is A, O, B. For the intersection, usually we say A and B. So and is the intersection, O is the union. But when you say A, O, B, usually in English, I think we get the idea that either A only, O, B only, right? බාහිර මම හරි කරනවා කෙනෙකුට දෙන්නව කරනවා කියන එක අයිති වෙන්නේ නැහැ නේ. You owe me. කියපුවම එහෙමනේ අපි අදහස් වෙනවා. මෙතනදී union intersection එකත් අයිති. Right? So that means this area is only A, O only B, O both. කෙනෙක් ඔක්කොම අයිති. මෙතනදී O කියන එක. But once you know the union, there is another word that you can learn, exhaustive events. Right? If maybe two events or more than two events, or even one event actually, I know for one event we usually don't talk about exhaustive, but two or more. If the union of several events is equal to the sample space, then we say we call those events exhaustive, right? Some people exhaustive, right? Exhaustive events, sample space exhaustive, right? So exhaustive events. In that case, you can have, sometimes they may have an intersection or may not have an intersection. You can have this kind of events. Union is equal to the sample space. So if that is the case, probably this is A1, A2, A3, A4. You can say they are not only exhaustive, they are also exclusive, mutually exclusive. Disjoint, they are mutually exclusive and exhaustive. එහෙම නැත්නම් මේක මෙහෙම වෙන්නත් පුළුවන්. A කියනකොට එහෙම තියෙනවා. නමුත් ඒත් union එක තාමත් S. ඒකට එතන mutually exclusive නෑ but exhaustive. Right? The is equal to the sample space. Right. So these are some exhaustive limits in general. Right. So now we know a little bit about events, right? Events are always we can define as a subset of some sample space, and then we need event operations to talk about the complex events. Okay, then thereafter we are now in a position to discuss about how to calculate probability. Right? So define probability first and then how to calculate. Let's take a small break and then